Welcome back. In this third segment, we're going to write our first proof of a big O relationship between two concrete functions. Now, assume you determine that the runtime of your algorithm is equal to f of x equals x squared plus 2x plus 1. And assume that you want to prove that the runtime of your algorithm doesn't grow any faster than the x squared function up to a multiplicative factor. So you want to prove that f of x is big O of x squared. Now, according to the definition of the big O notation, what your job is then is to determine which two constants c and k you can use to prove that the absolute value of f of x is less than or equal to c times the absolute value of x squared, as long as x is greater than k. So how to determine or to pick values for c and k? Well, one possible strategy is to start with k. So the first step is to figure out how to prove that f of x is less than a constant times x squared. I call that an x squared upper bound. Now, to find an x squared upper bound on f of x, it would be a good idea, maybe, to find an x squared upper bound on every term in f of x. So that will be the first step in this strategy. And if you do it right, it might be pretty easy to find the value of k for which these upper bounds work. Once you've done that, it will be actually very easy to compute a value of c that together with the value of k will work as a witness to the big O relationship. Now, I understand this is a little bit abstract, so let's actually start writing a concrete proof. In fact, we're going to write two different proofs, so here is the first one. So what we want to do is we want to prove that f of x is less than a constant times x squared, and we're going to try to prove that upper bound for each and every element of or term in f of x, and we're going to start with x squared. Now keep in mind that we're trying to establish the big O relationship for x large enough. In other words, for x larger than k. So the goal of this first step is to find a value for k that will give us an x squared upper bound. So again, as I mentioned, we're going to start with x squared. Well, x squared is the square of a real number, so it cannot be negative. Therefore, it's greater than or equal to 0. And of course, x squared is less than or equal to itself. So notice we just established an x squared upper bound for x squared. And it turns out in this case, we don't need x to be large enough, because this set of inequalities holds for any real number x. So in this particular case, there are no constraints on k, and let's record that. Now, we're going to try to establish an x squared upper bound on 2 times x for x being large enough. So again, we're trying to find a value of k for which that upper bound holds. So we need to do a little bit of work to prove this second step. So the first observation is that if x is greater than 1, then clearly 1 is strictly greater than 0, therefore x is positive. So if you consider the inequality 1 less than x, you can multiply both sides by x since x is positive without changing the direction of the inequality. So 1 times x is x times x is x squared. So we already proved that if x is greater than 1, then x is less than x squared. Let's write it down. And this is all you need to complete the proof in this case. So let's turn our attention back to 2x. Let's write down what we already know. X is strictly greater than 0, and x is strictly less than x squared, assuming, remember, that x is large enough. X is greater than 1. So that's the condition here. So what did we learn in this step about the value of k? Well, if k is equal to 1, we're all set because then x is greater than k. But of course, k could be greater than 1. If x is greater than k and k is 3, then x is clearly greater than 1. So what this step tells us about k is that k must be at least 1 for this set of inequalities to hold. So let's record this constraint. So actually, we're not quite done with this step because we need a less than or equal sign, not a less than, and we need an upper bound on 2 times x, not x. But this is easy to fix. You know that if x is strictly greater than 0, then it's also greater than or equal. In fact, you can always add an equal sign to an inequality. It doesn't work the other way around, but it works in that direction. So we can add the equal signs there, and since 2 is a positive integer, we can multiply those 3 numbers by 2 and keep the inequality in the same direction. And that gives us this result, which is perfect because it tells us that 2 times x is upper bounded by a function that is a constant times x squared. Assuming, of course, that x is large enough, meaning x is larger than k when k is at least 1. Finally, we turn our attention to the third term in f of x, which is 1. We also need to find an x squared upper bound for that term. We can use that result again, namely the fact that x squared is greater than 1, assuming that x is greater than 1 in the first place. So we have the same constraint here and the same restriction on k. Now to complete the proof, we must again add the equal signs on the inequalities. And now what happens is we have all the terms of f of x in the middle. We have x squared upper bounds for all of them. So we can simply add those 3 sets of inequalities. On the left side, 3 times 0 is 0. In the middle part, we have x squared plus 2x plus 1. That's f of x. And on the right-hand side, we have 4x squared. Now, of course, these relationships only hold if all of these constraints are satisfied. And what's the most restrictive constraint on x is that x is greater than 1. So here is what we just proved. For all x greater than k, f of x is less than or equal to c times x squared, and now we have a value for k, namely k can be any values from 1 up. So let's pick a value of k, say 1, and as I mentioned before, the second step is trivial here because the value of c is obtained automatically by this technique. The value of c is 4 in this case. Now, we're not quite done yet since we're missing the absolute value function, but the reason why I made sure everything was positive here is to guarantee that all of these numbers are positive. Therefore, we can add absolute values on all of them without changing the result. So we also proved that this is true. And now, we have completed the big O notation relationship proof that we were looking for. So make sure you pause the video and you review that proof in detail because you're going to have to perform quite a few of those. And this is just the first example. Now, the logical formulation of the definition of big O relationship starts with there exists C and there exists K, meaning there is at least one pair of witnesses, C and K, that will allow you to complete the proof. But of course, there could be many more than one such pair of witnesses. That's typically the case, so let me write down a second proof of the same big O relationship that will illustrate this point by coming up with 2 different witnesses for the same relationship. So in attempt number 2, we're still going to try and find an x squared upper bound for each term in f of x. Now for the x squared term, we can proceed exactly as in the previous proof. So I'm going to go fast. x squared is always positive or non-negative, and it's always less than or equal to itself for every real number x, so that doesn't add any constraint on k. Now, for the next two terms, we're going to do a little bit different reasoning. So let's assume in this case that x is strictly greater than 2. Well, therefore x is strictly positive, so we can multiply both sides of the inequality by x and still keep the order of the inequality. So 2 times x must be less than x squared. Now, if x is greater than 2, clearly x squared is greater than 4, so surely x squared must be greater than 1. So these are the two facts we're going to need to complete the proof. So let's do it. Well, first, if 2 times x is strictly less than x squared, we are very close to having an x squared upper bound on this term. So let's write it down. First of all, if x is greater than 2, 2 times x is positive, and as we just established here, 2 times x is strictly less than x squared. Now this is only true if x is greater than 2, so let's record that. So the constraint we have on x to be large enough is that k must be at least equal to 2. If that's the case though, we have this strict inequality, which of course implies the same one with the equal signs as we argued before. And now we have an x squared upper bound on 2 times x. Notice in the previous proof, 2 times x was proved to be less than or equal to 2 times x squared, as long as x is greater than 1. But if we're willing to go up to 2, we can actually establish a smaller or tighter upper bound on 2 times x, namely x squared. So we went from 2 times x squared down to x squared. That's just an observation in passing. Now we can use the fact that x squared is strictly greater than 1, and therefore positive, to write down this set of inequalities. We already established those inequalities here. Now these are only true, of course, under the assumption that x is greater than 2, so let's record that, and we have again the same constraint on k. As usual, we can add the equality sign here on the inequalities, and notice we now have an x squared upper bound on the 3 terms of f of x. So as usual, let's add up the inequalities. We get f of x is greater than or equal to 0, and the sum of these 3 terms is now 3 times x squared, down from 4 times x squared in the previous proof. Now, of course, these 3 inequalities must all hold for this addition to work. So in particular, it must be the case that x is greater than 2. And what we just proved is that for all x greater than k, f of x is less than or equal to c times x squared, with the values of k equal to 2 right here, and the value of c equal to 3 right here. And again, I added the absolute values without changing the inequality because all of these numbers are positive anyway. In conclusion, the main objective of this segment was to give you 2 sample proofs of big O relationships. Since you will have to write your own proof from scratch in this course, I strongly encourage you to study these proofs in detail and make sure you understand every step in them. Now, another point was to show that for a particular big O relationship, there may be many more than one pair of witnesses that will allow you to complete the proof. And a third point is for you to think about as you wrap up this segment. Notice the trade-off between the values of k and c. For the same big O relationship, when k went up from 1 to 2, c went down from 4 to 3. I strongly encourage you to go back to the graph I used to illustrate the definition of the big O relationship so that you can study the meaning of the values of K and C and get an intuitive understanding for why it is that when K goes up, C goes down, and vice versa.